everyone. Welcome to tonight's version of our FRC workshop series. We have First Team 3132, the Thunder Down Under, presenting tonight. We have Mel and we have Aman, who are going to be talking about advanced electronics. Mel's been part of FRC now for I think 11 years, and Aman, I don't know, 4 years maybe?
Yeah,
I think about right. So I will turn it over to the both of you. So thanks for being here.
Alrighty, thanks very much, Leanne. We'll get started here now. You can see that we're sitting here at Macquarie University at our home. I'm going to basically hand over to Aman and let her run the presentation for tonight. So I'll just get the screen sharing set up and then we'll be ready to go. If you're watching and you have any questions, just pop them in the YouTube chat. And I think we have a moderator over there keeping an eye on those. We are electrical people, so this is mostly going to be electrical oriented. If you do have any tricky software questions, I do have a software mentor on hand and you can save those questions up for the end if you've got anything like that. Alrighty, we'll just get started. Okay, and present and get back to the beginning. There we go. Okay, go for it.
Basically in this presentation, we'll be going through, I cannot see, our wiring tips, the JSD crimps, our data distribution table, a bit on pneumatics, sensors, encoders, and then we'll have the questions at the end, like Mel said. So essentially this part is just about some of the stuff TDU does for efficiency and keeping our wires organized. We like to coil and route our wire, so we'd recommend you think about where you want to route your wire to minimize rewiring and then ending up wasting time, which is really sad. We usually make a layout on wood or perf board first, usually perf board because it's good and reusable. It is a bit more expensive than wood, but in the long run, you can always reuse it and it makes cable tying stuff down a lot easier.
If you're not already familiar with perf board, it's basically just a sheet of polycarbonate that has regularly spaced 1/4-inch holes, which is great and lines up really well with all of the electrical components. You can buy it from AndyMark, and AndyMark usually stocks it in their Australian store, so you don't have to worry about the big shipping costs bringing it over from the US as well.
We will normally group wires going to the same place. So like you can see in the picture here, we're grouping all of the motor controller wires together. And we'll also tie wires down next to the component, and it just prevents them from unplugging when you're moving around in the area. And it keeps it more organized so you don't have to stretch wire.
So you can see in that bottom photo there, you want to just highlight where that cable tie is? Yeah, so we'll tie the wires down super close to the component itself. We sometimes call it strain relieving. It just means that if the wire gets caught up somewhere, there's a cable tie securing it down. So ideally it won't yank it directly out of the connector in the electrical component. So you can be a bit more confident when you're debugging that you don't have a lead unplugged somewhere.
Obviously, don't place wires near moving parts because it'll destroy them. We use stickies and again perf board to get to things like motors. Stickies are just like these things. You can put your wire on top and cable tie it through the holes here, and it just keeps things stuck to the side of the robot or underneath the robot wherever you can't exactly put perf board.
So we have a bit of a love-hate relationship with stickies. They're really good because they basically give you a mounting hole where there wouldn't ordinarily be one. So you can just peel the backing off, stick it down, and it provides you with a hole to run a cable tie through. They're usually sized to match up with standard cable tie sizes. On the downside, they don't work particularly well if you're pulling on a bit of an angle, and they can sometimes become detached. And sometimes the backing actually splits off and you're left with this horrible residue. So we have a bit of a love-hate relationship with those. We sometimes will alternatively, in our CNC parts, put in a series of holes specifically for cable ties, but that requires a heap of pre-planning. And if you change anything about your wiring, you're stuck with holes that you can't use. So we do tend to depend on them pretty heavily. If you are going to use them, you need to make sure you clean the area you stick them down to pretty thoroughly. We use acetone for that. You can use that on steel and aluminium, but you should not be using that on polycarbonate as it actually eats away at the plastic. But make sure the area is nice and clean before you stick the sticky down.
As for interference, it basically it changes and like messes with the signal going through the wire. So we'd recommend not putting sensor cables next to battery wire because they're very small and delicate, and the large current through the battery wire will affect the smaller current. We'd also recommend twisting your CAN and encoder wire. If you don't do that, you actually end up losing encoder ticks, which is really bad for software and especially for the auto part.
Yeah, so we have over the years had a lot of interference problems. Running your encoder cables next to your battery wires is a really big issue, but you can also have problems if you're running it next to motor power as well. So you want to, while you want to like bundle wires going to the same place together, you want to have one bundle for your power wires and one bundle for your sensor wires, and not run them with each other because you will get a bit of nasty interference between the two. And like Eman said, we also use twisted pair or twisted wire for CAN and encoder. If you're going to do twisted wire, so you're running two wires together, a really good way of doing that, if they come and they're not twisted already, you get one end and you stick it in a drill and you spin that drill up while holding on the other end. You spin it up to a nice tight twist, hold it there for a minute or two, release it from the drill. It will uncoil a little bit, but it will hold a pretty good twist along the length. So we do that for all of our CAN wire because we buy separate yellow and green wire and twist it together like that. Another way you can do that, and this is when you're talking encoder wire, particularly if you've got basically more than two strands, so 3 or 4 strands of wire, we actually braid that instead. It doesn't hold so well in a twist, particularly the encoder wire tends to be very, very fine and won't hold the twist as well. So instead we just get a couple of students sitting there for a bit of time braiding the wire together, and that works pretty much just as well as twisting it. We tend to do that for all of our encoder wires at this point.
When you drill in the robot, even though you said you wouldn't, a lot of things will fall onto really fragile elect components. So we'll often cover them with their own covers and elect tape, especially for circuit breakers. Their own covering isn't enough to protect the sides of the connector there. So there is a risk of like electrocution, which you don't want. So we'd also recommend covering the pins of the robo-rio, just because a lot of stuff falls in there, and if it does fall in there, it's a pain to get out, and it's a pain to realign the robo-rio pins.
Okay, yeah, actually, if you just go back. I can't go back. Sorry. Yeah, I just wanted to expand on that a little bit. It is really, really important that you cover all of your major electrical components if you are going to be drilling. So you want to think about that from the very start, like Eman said, and cover, like on the robo-rio, cover the DIO ports with a piece of electrical tape or something 3D printed. We have some 3D printed covers that we use, but be even more careful than that. So if you do need to drill, and in particular if you're drilling metal, as most of us are, put a piece of cloth over the robot to protect the electronics. And if you can, grab your vacuum cleaner and have the vacuum cleaner running directly under the spot where you're drilling to try and suck as much of the swarf in as you can. And if you combine all of those 3 things together, then you should be relatively okay. I will tell a horror story from a swarf incident that we had now a very long time ago in 2011, where we got swarf into our C-rio, which is the predecessor to the robo-rio. Goodness only knows what happened inside the C-rio itself, but the end result of doing that was our robot, which had no autonomous program, like we had never written one, started driving during autonomous. And we got some very confused FDAs investigating the situation, and the conclusion was it was because we had swarf inside the C-rio. So do be extremely careful with the C-rio. And then the PDP and the VRM are also vulnerable, so watch for those as well.
And don't drill over the box of elect stuff. That doesn't end well. We've made some standard 3D printed mounts for regularly used sensors and things we need to mount or cover, like we were talking about in the last slide. So that one's for the circuit breaker. This one we used to use for the robo-rio pins. What's this one again?
That's for an S40 encoder. Yeah, so we use the 3D printer extensively in electrical as well as on the robot in general to make just a bunch of different things. We have clips to hold PWM pins together, PWM housings together, and we print different mounts basically for all of the sensors that we use, so Hall effects and the S40s, potentiometers. A really important one, though, is the one that Aman's pointed to at the top. So the blue one up there is a mount or a guard that goes over the circuit breaker, so the main breaker itself. We have had problems, and other teams have had problems, where basically either another robot or potentially the game element for that year will get inside your robot and by some coincidence hit your main breaker and turn your robot off. And that has actually happened to us during a match. And so to prevent that, we 3D printed a guard that sits over the top. It allows access from the side so that you can still click the breaker in, and there's a hole on top that you can stick your finger through to turn it off again. But it prevents anything over a certain size, like game element size, basically, from getting in and accidentally switching you off. We've given out a few of those over the years, and we just usually keep a store of them with us, and we try and put them on every robot that we build.
We'd also recommend making your own cable. It ends up cheaper when you buy it in bulk. You can always adjust the length depending on where you want your wire to go. And you can use the crimps that you prefer, or whichever one suits your need best.
Yeah, so it's, as Iman has set up here, it's absolutely cheaper to do this. Rather than buying the pre-made ones, which come from Andy Murray, can come in 12-inch, 24-inch, 36-inch lengths or anything like that. And you're stuck with those lengths, and they are expensive because they have been pre-crimped. It can be less expensive if you commit to doing this, to going and buying the wire, the crimps, the housings, and the crimping tool. And over a certain amount of time, it eventually becomes cheaper than just purchasing those off-the-shelf ones. It also means that you have an adjustable length. So we will crimp one end of the cable, run the cable, figure out where it's going to, cut it off and crimp the other end. And that means that we don't have, or we try not to have big bundles of unnecessary excess cable just stuffed inside the robot. So that's really helpful if you're trying to keep it neat. It also means that, if all you've got left is 12-inch pieces, you're going to have to string them all together, and you've got a bunch of disconnect points that you don't want that are vulnerabilities. If you're making your own ones, then you can run it the full length or to whatever disconnect point that you actually want, and cut down on the number of connectors that you've actually got in that run.
We'd also highly recommend using good tools, especially our favorite angled side cutters. These basically help in cutting the cable tie flush, so that you don't, scratch your hand while you're fiddling with the components. And it also prevents cable ties, the extra ends, from obscuring your view of whatever you're working on. We'd also recommend using ratcheting strippers. I think they're better for holding the wire. And correct crimpers for ring and spade crimps, and a designated pneumatics tubing cutter. Ours doesn't exactly look like this, but it's really good because you need something sharp and you need something that'll give you a clean cut so that it goes into the connectors without jiggling up and down.
Yeah, so if you're going to do your own wire length, so if you're going to do your own crimping, this is absolutely 100% necessary. And if you're going to buy anything, I would suggest buying the ratcheting strippers. They make such a difference. It means that stripping the wires is super quick. It basically can't go wrong. And those things are just super useful to have around. Sharp pair of wire cutters is really important as well. And you want the type that is flush on one side so you can cut the cable tie off dead flat across the head. And yeah, as we've set up here, getting the correct crimpers for the ring, like the yellow, red and blue ring and spade crimps, is really important. I've seen people in the past without those crimpers trying to do them basically in the corner of a vise. You clamp it up nice and tight in the vise. It does work, but it's not giving you a quality crimp on that. So they're not FRC specific crimping tools at all. You can get them from RS or JCar or somewhere like that. And it's a really good thing to have if you're going to be using the ring crimps, which I think are necessary for the spark motor controllers. Just a really good investment over a couple of years of doing this.
We use some extra things that help us with efficiency and just keeping things neat and efficient again. We have a couple of these Andy Mark tape dispensers with a bunch of different colors for color coding, which we'll talk about in a minute, I think. They're great because you can just cut whatever lengths you need. We've used Echain in the past that keeps the wires going, for example, on a lift. It keeps them grouped together and prevents them from going into other components. We have the thrifty throttle, which is fantastic for testing elect components rather than connecting everything to a big motor controller and doing it from there. And we have the battery beak, which is, that's the one that like tests the battery, right?
Yes.
Yeah.
Yeah, so these are just things that we've sort of accumulated over the years. I'm sure most of you have a piece of Echain at this point. It usually comes in the kit of parts every year. I would suggest keeping all of the stuff that you've been given, and if it turns up on first choice, trying to get some more. If you ever want to build anything that requires wiring out on the end of the arm, or like Iman said, on a lift, you're going to want the Echain. The stuff that comes in the kit of parts is pretty decent. You can't, to be fair, get that much through it. You're only going to get a couple of power wires, maybe a PWM. It is commercially available though, and you can buy different sizes. We have done that in the past. It gets a little bit pricey, so if you can just accumulate as much of the stuff as you can through your kit of parts through first choice, that's a really good idea. The thrifty throttle, absolutely fantastic. If you want to do some testing and you don't want to get a RoboRio involved, a thrifty throttle lets you adjust the power going to a motor really easily, so you don't need any software. I know our software team doesn't want to get roped into the mechanical testing most of the time, so that's super useful to have. And then the battery beak is super important once you start collecting, once you start accumulating a lot of batteries. It tells you the voltage of the battery, but we also use it for the fair good poor rating that it gives. So after you've had a battery for a couple of years, you want to know if it's still good, then that's a really easy way of just checking the quality of the battery at that point.
We use 775 Aussie Boards for 775 motors to avoid soldering wires, which just gets really messy. And also soldering wires is just a big pain onto these. They just make the process of like communicating between the motor and software just a lot easier.
Yeah, I can highly recommend these components. They come from Australia, I believe.
They're like $5.
Yeah, they're pretty cheap. And they're just much easier to use than actually having to solder a wire onto the 775. The other nice thing is they point the Anderson connector the other way, which makes it really easy to secure the wire to the side of the 775 if you want to. Yeah, and they're just a really good build quality as well. So we now pretty much exclusively use those on our 775s. Highly recommend getting some of those.
We're going to talk about JSD Chromes, which are kind of, our alternative to the regular standard PWM crimps. We do have the RS part numbers for the actual crimp down here. Essentially, they just look like that. There's a separate male and a female crimper. They work pretty much the same way as a PWM. You just don't have to hold the crimp inside the crimper. They are extremely expensive though, which we'll get onto here. There's some pros and cons between PWM and JST. Obviously, the housing is more secure compared to the older crimps. You kind of have to press this down.
So there's actually like a little clip that clips over on one side and means they can't be pulled apart. As most of you would be aware, the PWM housings don't have anything like that. And you can see in the photo, we 3D printed a housing, the yellow thing that holds them together. But if you use this JST type, it has that clip inbuilt into the housing itself.
They can only plug into each other one way. Obviously, once you've crimped it, you can't plug it in backwards. And they're industrial grade, so they're very reliable. We've had them for about 2 or 3 years.
Two seasons, yeah.
They're basically mint condition, which is really good. They are quite expensive, $470 US, which gets to about $660 Australian dollars, which is quite a lot. And the crimps are like 10 cents each, which is a lot as well. With the crimping, there's only like one slight inconvenience with it in that the yellow and green wire can only go into one port. They are labeled, but it's kind of hard to see. And if you've crimped the yellow into the wrong hole, you have to recrimp it.
Yeah, so as Iman said, these are very expensive. Just to give you a bit of background, we used the PWM crimps for 9 years and then switched over to the JST 2 years ago after having a number of issues on the field and during testing with the PWM crimps and the housings. The main issue, as many of you know, is the housings are disconnecting from each other. And we've tried a multitude of different ways of trying to keep them together. So at one stage, we were putting electrical tape all the way around to hold them together. Played a bit of a joke on ourselves a few times by using black tape and then not being able to see it later on and wondering why they weren't coming apart. We then switched to 3D printing these housings that hold them together. But you know, the electrical tape, you can sometimes actually separate the housings and not see because the tape is there, and then you don't know there's a problem. And even in these 3D printed housings, we would sometimes find them slipping out as well. And so this was just causing us so many problems over the years that we looked for a different solution. The JSD crimps were recommended to us, but you know, we started using them in our 10th season basically. So we'd been doing this for quite a while before we were looking at something as expensive as the JST crimps. I think it just, you know, goes to show that it's really important that you have a good debugging process. So we were able to trace all of these problems back to the fact that the housings were coming apart, and that you think really, really carefully about how you keep your housings together if you are using the PWMs. This is also true of other types of crimps as well. So obviously most of us use or a lot of us use the Anderson power pole crimps for our motor power. Those, although they do click together, can still become separated. So we've started, you know, threading cable ties through the holes to hold them together. We've even had issues with the battery Andersons coming apart. And so now we will actually cable tie those in place as well. So that's just something to think about if you're having electrical problems and losing communications to particular motor controllers, or you're losing power. Often what we have found is the problem comes back to the housing actually having separated. You may have plugged it in right at the beginning of the process, but over the course of a match, it's been shaken around and it's come undone, or maybe it wasn't plugged in properly right at the start. But this has been a really big problem, and this is one of the ways that we've been solving that recently.
I'm going to talk about our data distribution table. Basically, it's just a Google Sheets table, which it outlines the subsystem, the CAN ID, the motor going to it, the fuses for the PDP, and the color that we've labeled it. It basically helps software mostly, and it helps us to know which wire goes where, and it improves communication when we're not there and software's working on the robot. And we have different sheets for every component, PDP, CAN, RoboRio, etc. Just to keep everything organized and in one place. We have double colors for the same subsystem, and color coding is by subsystem, not by motor.
Yeah, so the data distribution document is something that we've had going back probably 5 or 6 seasons now at least. We still have all of the old documents. We set this document up as a Google Sheet and then share access to anyone that is going to need to be able to see where different things are plugged in on the robot. And this is actually one of the first things the electrical team will do in the course of a season, is set up a document. So like Iman said, we have a page where we list out all of the PDP slots, all of the CAN IDs, all of the inputs on the RoboRio, the slots on the PCM, and the slots on the VRM. And the first thing that Elect does basically the entire season is talk to all of the other teams, figure out what they think is going on the robot in terms of the motors and their power requirements, any sensors that are going on, and they start planning where on the PDP those motors are going. So do they require a 40 amp slot or a 30 amp slot? And also thinking about all of the sensors and what types of sensors are they plugging into Talons? Are they being sent back to the RoboRio? If you're using pneumatics, what type of solenoids you're using, and how many slots they're going to take up on your PCM. And they start plugging in all of this information into this sheet, and then they start color coding it. And that color coding comes back to that AndyMark tape dispenser that we put up a couple of slides ago. What we'll actually do with that is when we physically run these wires later on, is we will then go and tape the wires with the corresponding color from the sheet. So someone who has had absolutely no involvement with the wiring of the robot can open up the document, look to see a particular subsystem, where that is plugged into the PDP, any sensors if they're going to the RoboRio, if that system uses any pneumatics on the PCM sheet, look for the color that it's been assigned, and then look into the robot until they find a wire of that color. And that way you know which wire corresponds to which motor. So that's incredibly important when we're doing testing and debugging. And like we've set up here, this is really important for the software team. If there's no one around from electrical and they need to do some debugging, they open up this document and they can much more easily figure out how the wiring is working. So this document has been really, really important for us. It's also important as a sort of a legacy document as well. So we keep many of our old robots. And if we ever want to get those running again, we often do for demos and things like that. And we've kind of lost track, or some of the students have actually moved on from the team. We still have these data distribution documents going back 5 years. We can open them up and we can actually figure out how we wired that robot 4 or 5 years ago. Makes that much easier as well.
We also color code both at the PDP or the CAN, wherever it is, and then we'll color it again at the actual subsystem. We have like designated colors for every subsystem that we kind of reuse every year as well. This is about our pneumatic system and what we do that kind of keeps our team going a bit smoother. Sure.
Okay.
Yeah.
Okay, so the first, something that we have switched to, again, probably in the past 3 to 4 years, is using a solenoid manifold rather than individual solenoids. So when you start out with using pneumatics, you've probably got just 1 or 2 on the robot, and it's enough to just have an individual solenoid controlling that pneumatic. As your pneumatic systems get more and more complicated, you could end up with as many solenoids as you can plug into a PCM. So, you could potentially have, 4 or 8 if you're running 2 PCMs on the robot. And that's a lot of solenoid to mount. It's a lot of plumbing to deal with as well. And so what I've started to do instead is use these solenoid manifolds. So these are components that actually let you screw in. They come in different sizes. You can get a 3-slot, 4-slot, 5-slot, or 6-slot manifold. So the number refers to how many solenoids you can mount onto them. You do need a special solenoid to mount on, but you mount on the number of solenoids that you need for your robot. And it centralizes all of the plumbing that's coming out of the compressor and everything towards that end, goes into the manifold, and from the manifold goes into the solenoids and gets distributed out. So as we've set up here, it just makes everything much more centralized, so you can keep your compressor and your gauges and your regulators and your tanks and all of your solenoids all in a central location, which is what we prefer to do for troubleshooting purposes. And it also means that all of your solenoid wiring as well is starting at the same place, and it's easier to then run that back to your PCM. And it does cut down a little bit on the number of connections in the system, which is good because, as you know, if you've used a pneumatic system, the biggest problem you're going to encounter is something not being plugged in properly or being twisted or bent and coming out, and then you just having a catastrophic pressure depressurization, basically. So this helps with reducing the number of connections that can go wrong. And so solenoid manifolds are something that we've found to be really useful in the past couple of years. They're also just way easier to mount securely than an individual solenoid. So a really good thing to be thinking about if you're going to be using more than 2 pneumatics on your robot.
We would like to point out that obviously solenoids can be better when they're closer to the operating part and you don't have to run tubing all the way through your robot. And it's better for identifying what goes where, what solenoid corresponds to what, and faster testing if you just want to check a small component. If you are using a manifold, make sure you label your solenoids in your tubes, and it can get really confusing when you have several tubes. So we usually use the same color coding tape, I think.
Yeah, so that goes back to that data distribution document. Whatever system and color code that we assigned to the PCM and to the wiring that runs from the solenoids to the PCM, we try and use exactly the same color coding on the pneumatic tubes themselves so that you're always confident about what system you're dealing with. We also like to try and color code the in and out line of the tubing as well. It just makes it a lot easier to debug. You can do that, well, we do that in 2 different ways. One way is to add either a black or a white stripe to the color coding to indicate one way is in or one way is out. The alternative is, First Choice supplies an endless variety of colors of pneumatic tubing. So we will get 2 different colors of tubing. Actually, we often get 3 or potentially even 4. We use one for going one way past the solenoid, one for the other way. And then before the solenoid itself, we use a third color on the low pressure side of the regulator and a fourth color on the high pressure side. And this makes it much easier to figure out what's gone wrong when you're debugging or testing. If you've got something coming unplugged, you know, if you're dealing with a section between the compression and the regulator to the manifold, and then past the manifold or the solenoid, which direction we're looking at. So that's really helpful there.
We're going to go through some of the sensors that we've used in the past and what we prefer to use. There's, of course, the limit switch. This comes in the kit of parts, I think.
Kit of parts, or you can get about 100 of them in first choice every year if you use your credits correctly. Wouldn't advise doing that. Sometimes you can have too much of a good thing.
Limit switches are great. They're a bit different to a Hall effect, which we'll talk about in the next slide. They use PWM wiring, so you hopefully have the facilities for that. They're quite easy to use and very easy to code for because there's only two cases, on and off. We use these in the hatch, which is what you can see here last year in the 2019 season, to detect like when we had the placing of our hatch.
Yeah, so we had a system that moved back linear back and forth, and we were using these to detect when it had reached the endpoint. You can get two different kinds. So the one in the photograph just has like the individual bump button, whereas the one in the top photograph has the arm. So yeah, they're primarily used as hard stops. If you use the one with the arm and you pass your component just past the arm, you can trigger the arm without smacking into the limit switch itself. It's still a little bit risky. If you're using the one with just the bump button and you overshoot, there is always the risk of basically smacking into the limit switch and causing some damage there. We will talk about the Hall effect, which is an alternative that avoids that altogether. But you know, the limit switches are cheap or free through first choice most of the time, so they are a really good option. So really inexpensive, really easy to program, really easy to wire, but they do have some issues and so we prefer most of the time to go with alternative sensors, but we do still have some uses for the limit switch.
The Hall effect sensor is the alternative. It's basically a limit switch that doesn't involve hitting the actual sensor. It's essentially just a magnet sensor. It switches on when it's in front of a magnetic field. We use it on our lifts and it tells us when we've reached the top or the bottom. We can use them for levels on the lifts as well, if you're planning on doing that.
Yeah, so we built a number of lift robots, obviously, since 2015. Recycle Rush was our first one, and pretty much every year since then, we have at least considered using Hall effects on the lift system. Basically, you have the sensor itself, which is what you can see in both of those photos, and the sensor will be triggered when it detects a magnet passing in front of it. And so no contact is required. It doesn't need to be an end stop because of that. It can actually go past. And so on a lift system, we may actually install not just one at the bottom and one at the top, but maybe 2 or 3 in the middle, which will allow us to know at what particular point along its height the lift is currently positioned at. So if you just want to be at one of 3 different heights, the Hall effect sensor is quite a good thing to use there. Obviously doesn't tell you incrementally where you are. It tells you when you've passed a particular level. You can see in the photo that it plugs in with a PWM wire. So again, these are really, really common. This goes back to, you know, you really want to be making your own because often these Hall effect sensors can be a really, really long way away from the Robo Rio, and you're going to want to run quite a long cable to them. And so it can be really useful to be able to make your own lengths. Some difficulties with the Hall effects. Firstly, probably the biggest problem is it's got quite a limited range. So you need to be very precise about how far away that magnet is too close, and it will just wallop the Hall effect sensor. But you go like 2 millimeters further away than that, and it actually won't pick up on it. So you need to get it in a very, very precise distance from the Hall effect for it to actually trigger at that point. The other issue is that the sensors themselves are quite delicate. And can be fairly easily broken. So like we've talked about before, we usually 3D print a housing or a mount for them that just makes them a little bit more stable and a little bit more secure.
We also use the beam break, which essentially is just an infrared beam. If the beam breaks, the switch deactivates. It's basically like an extension of a circuit. It's kind of like the sine B lasers going through. It's the same idea. We solder LEDs on so we can actually see the laser beam without having software check if it's on and off. And it helps to find electrical or mounting faults early. If it's not working, then we know. We've used it in the shooter in the past to tell us how many balls we have within frame perimeter or to see if anything is in the flywheel.
Yeah.
I think we're using it in 2020 as well. That's
we
where
might
this
have
one's
some
off.
on the hopper. Yeah, we've been using these for now about 5 years. I think the first time we implemented them was for the Stronghold game. They're basically gates. They know when something has passed between them because the IR beam is being broken. So they have two halves. They have the emitter and the receiver. And so one sends out the signal, the other one's looking for the signal. And if it doesn't pick it up, it knows there's something there. So it's really good for detecting if you have a ball passing through a conveyor belt or something like that, knowing when it's gone through or counting the number as they go through. You do have to bear in mind you've got to mount the two different components of it across from each other with the correct line of sight, because if they're off axis, they're not going to see each other. So you've got to be quite careful like that. And then, as Eman said, we do often solder an LED into the system that will tell us when it's on. You can't actually see in the IR beam just by looking at it. It's not visible. And so if you're encountering a problem in that system, it can be hard to debug because you can't actually tell if the beam break is functioning. So we will put an LED in the system that will light up when it's working. An alternative that we've used a little bit is some phone cameras will actually be able to see the IR signal as well. So if you look through your camera, I think it works, or this is true at least a year or two ago. It works on Android phones, but iPhones actually filter it out. So you can look at the beam break with an Android phone camera and see if it's on. That's an alternative to putting the LED in, because as we've said, debugging this can be a little bit tricky. These are super useful though, because you're detecting something going through without making any contact. They've got a reasonable range as well, so you can usually get a medium-sized game piece between them. So a really good option for counting or detecting a game piece as it moves through the robot there.
So Android cameras have a use. We have the NavX, which is basically this board here that we put onto every single rubber rear that we've ever had. It doesn't come with the kit of parts,
but you can get it through First Choice.
Yep. It helps with calibration. It acts like a gyro. It essentially tells you where you are, how you're turning. Really helpful for software. And it's on every rear that we have. It's pretty easy to mount as well. There's just 4 screws and it goes on.
Yes, we use that extensively, particularly during autonomous to guide the robot. One warning that comes with the NavX is you'll see in the top photo that it does have a number of pins coming out the top, and we have on a number of occasions accidentally crushed those by dropping something onto the robo rear, which you shouldn't do anyway. But the robo rear without the NavX is slightly less vulnerable to that. So it is advisable, if you can, to come up with some kind of cover. We will 3D print things potentially to go over the top to protect the NavX pins. It's just really difficult to bend all of those pins back in. Like I said, I think you can get them most years through First Choice. There's usually a couple up there. Otherwise, you can get them from AndyMark. If you're planning on doing autonomous that does basically anything more than drive forward for X number of seconds, then you'll want to be looking at the NavX or something like a NavX to guide your robot for that.
This is my favorite slide. These are some sensors that we've used in the past or haven't used. We got them randomly. We don't use them because they're quite unreliable and they don't work all the time. This includes my favorite, the push switch. The retroreflective that we used one year, but it didn't work properly for us, so we don't use it again. And the ultrasonic. This is on FLL. It works good for FLL, but not for FRC, unfortunately.
Yeah, so we do have a number of these. We've actually got a ton of the ultrasonics. I think we used it successfully in 2014, although I can't recall why. We tried to implement it in 2016. If you remember the Stronghold game, we had this wonderful idea that we would have 4 ultrasonics facing out the sides of the robot, and they would tell us when we had passed through particular defenses, because most of them had sidewalls. Turns out the driver can actually see that very, very well. And And so we ended up, I don't think we mounted them and then didn't actually connect any of them up. There are just a lot of other sensors that tend to be more reliable or easier to work with than these ones. But you will see these often, particularly on first choice, coming up as options. So if you do see those, I would advise using your credits elsewhere.
We're just going to go through some encoders. All of these are rotary encoders. We'll start with the Andy Marks encoder. Essentially, it attaches to a SIM and obviously works as an encoder. It's inbuilt in the motor, so I don't think you need to put it on mostly.
You can.
You can if you want. We don't use them because we prefer S40s. Secondly, we have the SRX Mag Encoder. We used this in 2018. It's quite small and easy to put on. It plugs straight into the talon, and the magnet, it uses like a magnet to detect how far you've gone. You can't centralize a leg with them. Things need to be really close to each other, especially the magnet and the wire from the sensor must be short or it ends up frying the talon. Like the precision required to keep the spacing at the right point is kind of hard to get to.
Yeah, so these are absolute encoders. We have used them in the past successfully, but they are quite difficult to actually fit onto whatever system that you're using them on. For two reasons. First, like Aman said, it needs to be very much like the Hall effect sensors at a very specific distance between the sensor and the magnet. Otherwise, it simply will not pick up on it at all. And then the other thing is actually mounting the magnet into a shaft. So we put them into shafts that were driving some intake arms in 2018. You need to have a central hole in the shaft of a particular depth, again, so it doesn't slip too far down. So because it needs to be so precisely centralized, you're needing to basically manufacture that axle probably on a lathe. So if you don't have access to that type of machinery, you're going to run into some difficulties in drilling the type of hole that you actually need to mount the magnet in the first place. If you can achieve that, they are fairly reliable and nice to use, but you need to be very cautious that that magnet is staying in place.
These are the ones that we use most often. The E4T and the E4P are basically just different models of the same thing. They are for wheels. They're different models. Sometimes they have different clicks. They're all the same type of encoder. We do use a digital breakout board between the sensor and the talon, which just is mainly for accessibility between the types of inputs that go into here and the inputs that you need for coding.
Yep, so we use the S40 encoder. Many of you will be familiar with the E4T or the E4P. I think those have come in the kit or in first choice in previous years. Maybe it's first choice. The S40s don't. These are ones that we buy especially, and you can see a picture of that at the bottom. You can see that that's obviously got the sort of the encoder housing on the left-hand side, and then it's got the shaft that comes out. So you need to interface that shaft with the axle. In our case, that's usually a drive axle. There are two ways of doing that. The first one is you actually push the axle, the output there, into a hole in the axle, and it needs to grip and stick inside that. We have done that in the past. You need to drill a central hole, again, on a lathe. You need to make it a very, very precise size so that there's enough grip on the shaft itself. If you drill a hole that's too big, can be problematic. You can solve that by wrapping it in a little bit of Teflon tape sometimes. But we have actually found that if that hole's a little bit off center or a little bit misaligned, it can actually result in severe damage to the encoder. So what we have moved towards now is not having a hard push in connection of the shaft into the axle. And what we do instead is we situate the encoder a little way away from the axle, and instead we run a piece of heat shrink from the output of the encoder to a little bit stuck on the outside of the axle, so a little nub that sticks out of the axle. We heat shrink those together, and that usually provides enough of the connection to turn the encoder. But because it's heat shrink and it's flexible, you're not going to have problems if the sensor wobbles a little bit. and it's no longer concentric, you're not going to get damage to the encoder. So that's what we've moved to most recently, and we found that it basically results in better reliability for the S40s. We don't have problems where we break them anymore. The S40s are quite expensive. We have had some issues importing them in previous years, but we do find them to be quite reliable, and we use them fairly extensively on all of our robots now. We have looked at alternatives. E4T and E4P is a more accessible and cheaper alternative.
Lastly, we have the potentiometer, usually better for small game manipulation sort of pieces. It measures the angle that it's been turned. It can only spin between a certain range, unlike the encoders that we talked about before. It's good for like wave-like motion, and you use an analog breakout board instead of a digital one between the sensor and the whatever you're trying to move.
Yeah, so the main limitation on the potentiometer is that it only operates between a certain range, so it's a full rotation or thereabouts. Won't go beyond that. If you do force it beyond that, it will just break the encoder.
There are also 10-turn buttons.
Okay, thank you. You can get ones that go more than a single turn, but you will always find that they do bottom out at a certain limit. It just depends on what that limit is. We have used them a little bit. The big problem is that people will forget where the endpoint is, not reset it properly if they're doing some maintenance, and then we will run an autonomous routine or something during a match. We'll go past that end stop, we will break the potentiometer, and we have done that countless times. So if you're going to use these, you need to have a really careful routine about resetting them and making sure that the potentiometer is positioned correctly relative to the end stop before you start running any code on the robot.
I think that's about it. If
Okay.
there's any questions.
I will just add in, I got a note over the course of the presentation to add in something about the PWM crimps. So another reason that we moved to using the JSD crimps was because we did identify a second problem with the PWM crimps, which was that even when the housings appear to be still together, the PWM crimps are cheaper, lower quality, and will actually not be in contact sometimes, even though it appears that because the housing is plugged in that they should be in contact.
Bounce.
Yeah, they'll bounce and they'll separate as the robot is moving, and you'll lose connection because of that, which is a really big problem because it happens when the housing is still connected and you cannot tell that that's what the problem is. There is no way of knowing that that's what's happened because there's no physical evidence that they've actually come out of contact. It looks like they're still connected. And so that's another reason why we moved away from the PWMs to the JSTs. So if you are having problems with what you think is your PWM cable and you cannot find physically what the issue is, that's something to bear in mind. It can be because the pins are actually losing contact even when the housing is still connected. Okay, I think
it's also
that's
like a little bit harder to know if the actual crimp is inside the housing because the click is not audible at all.
Yeah, the JST connectors are very, very clearly labeled, and there are far fewer mistakes to be made regarding plugging things in backwards or installing them incorrectly in the first place because there is so much labeling. Because of that clip connector, they only go in one way. And like the PWMs, you can actually buy them for different pins. So you can buy 2-pin and 3-pin. That's what we have on hand. We use the 2-pin for CAN and the 3-pin for PWM. You can get 4 and upwards. That's also true of the PWM. You wouldn't find those on AndyMark or an FRC supplier necessarily, but you can look on other websites like Hanson Hobbies and find different pin numbers. So the JSTs are just as flexible as the PWM in that respect in particular. Okay, I think that's all that we have to talk about for today. We might go and see if we have any questions at this point.
We do have a few questions. The first one I think ties back to what you were just talking about, in that, if you do have some electrical problems, how would you approach debugging those?
Do you want to take this? Yeah. Okay. So yeah, when you're encountering electrical problems, first of all, you want to have your multimeter on hand. So if we're losing, it depends on what the electrical problem is. So if you think that you are potentially losing power to a motor, or you're not being able to send a signal out to a motor or a system like that, You first of all want to have the robot turned on blocks, and you want to have software run through whatever routine it is that they're doing when they're encountering the problem. And you want to be looking really carefully at your Talon lights in particular to see whether or not your Talon or your motor controller is actually receiving the signal you think is being sent there and behaving appropriately. So you should be able to identify right off the bat if the problem is somewhere from the Talon to the motor. So you're getting the appropriate light coming out of your motor controller, but your motor is not behaving normally. Or if your motor controller isn't behaving the way you're expecting, then the problem must be further back. So have all of the reference documents on hand for all of the motor controllers that you're using, know what the codes are. That's really important in terms of determining what a problem might be. You're getting lights on your motor controller, you need to know what they mean. If your problem is between the motor controller and the motor, what you probably want to be doing at that point is a physical inspection of the wires. Usually it's between the motor controller and the motor that you have the risk of a wire being cut through, because those tend to be the vulnerable wires. So you want to do a visual inspection, making sure that all of your connectors are still plugged in, that there are no cuts or damage to the insulation as well. And also, if you've soldered to your motors, that those connections are still really strong. And often what you will find, if the problem is downwind of the motor controller, something has been cut through or something has become unplugged. So that's what you would be looking for after the motor controller. If it's before the motor controller, you still want to do a visual inspection, because there's always a risk with a bit of vibration that something has become unplugged or you've got a bit of damage. You can use a multimeter and do a continuity check if you think that there is potentially a break in the wire that you either just have failed to identify, or if you have run the wire inside a piece of tubing or a piece of Echain and you simply cannot see. You get out your multimeter. Pretty much every team in Australia has the same Fluke multimeter, because they keep turning up in first choice. If you don't have one, put it on your list for next year. Put it on the continuity check setting and check each end of the wire and make sure that you have a connection all the way through. You'll often find that something again has gone wrong with the connector there. At that point, if you're not seeing a problem between those two ends, then you want to go and double check that everything is all right with all of your components. So has there been any physical damage to the robo rear or anything like that? You want to double check the way you have actually run the wires. If you think you're seeing a sensor problem, have you actually run your sensor cable next to a power cable and what you're seeing is actually an interference problem? So go and have a look at that. And at that point, if you still can't identify the problem, it might be time to go and talk to the software team and get a bit more information about what they think the problem is and make sure it's actually an electrical issue.
And always check if your CAN is in the right way and your power cables are in the right way around.
Yeah, when you're checking your connections, always make sure that you've got yellow to yellow, green to green. You haven't reversed any PWM cables. We've caused a few problems for ourselves by doing that as well.
Great, thank you. Another question that came in is, they would like to know how reliable the heat shrink to encoder is. Has it ever failed?
Heat shrink to encoder. No, we have had absolutely no problems with it if it's been done correctly. So you need to make sure that you choose the correct size of heat shrink for the output of the encoder. You want to make sure that the nub coming off of the axle, I might just stop sharing. Okay. Yeah, so you want to make sure that the nub coming off of the axle is the same diameter as the shaft coming out of the encoder, and you need to make sure that you pick the heat shrink appropriately for those sizes, and then you just want to make sure that you have shrunk it down the whole way around. So rotating as you go, make sure you get the appropriate amount of shrinkage on the heat shrink. If you do that, then under those conditions, we have had absolutely no problems with that method. And like I said earlier, we found it to be much better than physically pushing the encoder into the shaft. Doing that has actually resulted in us losing hundreds of dollars worth of encoder through breakages. So heat shrink all the way.
Great. The next question is, have you shared the design files for the circuit breaker protector?
We haven't shared them, but we could do if I can find where they are. Yeah, I would be happy to share those files. We could potentially upload it somewhere like Thingiverse, or we could we'll figure something out. We'll make them available and let First Australia know when those are available. They're pretty fast and easy to print. They don't use much filament. So yeah, we'll make those available.
Yeah, we're happy to send that out through the FRC Australia group if you let me know where they are. So
Yeah, absolutely.
easy. All right, one more question, which is, what are the advantages of a centralized versus distributed set of motor controllers?
Good question. Okay, so yeah, when it comes to planning your layout at the very beginning of the season, when you're looking at your initial robot design, you'll go probably one of two ways. You'll either put all of your motor controllers right next to the PDP, so you've got super short runs going to them. You don't need any extra Anderson connectors. They're all in the one place. And then from there, you send power and signal out. The alternative, so that's centralized. The alternative is distributed. So you position all of your motor controllers close to whatever the motor is that they're controlling. So these are on the ends of arms, at the tops of lifts, distributed out on top of your gearboxes for your drivetrain. So that's a distributed system. And those are quite different in terms of the layout. We have used both over the years. We tend to go for the centralized system, but we have found at times that we need to go, at least some motor controllers need to be distributed. The advantage of having them centralized is that, well, there's a few different advantages. If they're centralized, debugging becomes much easier because you can see all of your controllers at one time. So if you're trying to debug a big problem, you're going to be able to see all of the lights on all of your motor controllers at the same time. And so that makes debugging much easier. The other thing that we've found quite good about that is it often allows you to build a single electrical board that can be built off of the robot while someone else is building the robot itself. You've got your electrical team working on the board, which is sat down somewhere else, and then you can drop and plug that into the robot. If you want to change something later on, you can unplug all your connectors, take it out, make some changes, put it back in. And so that can be very nice in terms of enabling different groups of people to work on different aspects of the robot at the same time. The problem with that can be it means that if you're running sensor wires back to your talons, those sensor wires would potentially need to be very, very long, particularly if they're out on the end of the arm or the top of the lift. And sensor cables basically do not want to be run in very, very long lengths. We've actually, I think we mentioned this earlier, blown out a couple of talons at Champs a few years ago, completely dead. We took them over to the guys at VEX. They couldn't fix them. They gave us new ones. They said we had killed them completely by running a sensor cable that was too long. I think that was to a Mag Encoder. And so if you're going to be running one of those gray ribbon cables into a talon, for instance, that is a case where you would probably want to distribute your motor controllers out and sit those motor controllers close enough to the motor that you can use a short ribbon cable to run the encoder back to the talon. Otherwise, you're going to encounter problems with that. So that's where we go for distributed. We don't usually go fully distributed. We go individual controllers that have those ribbon cables further out. I would imagine that you might also you could potentially go for a fully distributed system if you've designed your robot in such a way that you simply do not have room next to the PDP to get them all in at the same spot, and you'd send them out all across the robot. But I really do think that makes debugging a lot harder.
Great. Well, that seems like that's all the questions that we have. Do you have any closing words or remarks?
Not really. No, thank you very much for joining us tonight. I hope this was useful. If you do have any questions or you would like to see more of anything that we have talked about tonight, so we'll share that breaker guard with you. We do have other sensor mounts as well, files for that, if you're interested in anything like that. If you want to know where we purchase any of our parts from, so we do make all of our own cables, we have suppliers for that. Happy to let anyone know where we purchase any of those items from as well. Yeah, so if you would like to know anything more about what we've talked about tonight, just let us know.
Great. Well, thank you so much, both Mel and Aman. That was wonderful, great information. I know we have a lot of people who are very, very happy to have tuned in for the night. I also want to say thank you to our behind the scenes crew as usual. Tonight we had Ian from IC Robotics helping to monitor the chat, and we had Lyndall and Andrew from Project Bucephalus sort of on secondary backup for that. So huge thanks to all of them for making this happen. I hope you all had a great holiday weekend, and yeah, we'll see you next week. Bye.
Thank you for having us on, Luann.
Okay.
Bye-bye.